Welcome back, ChemStars. We're on Chapter 3, Video Notes, Page 3. It's our second video. And now we're going to look at the structure of the nuclear atom. So here is our I can statement for this section. I can evaluate the critical contributions of scientists and the experiments that led to the development of the atomic model. We're going to be focusing on the importance of models, and some of the key vocab words are going to be atom, element, billiard ball, plum pudding. You might think, wow, that seems weird. We'll get to it. Cathode ray tube, electron, gold foil, nucleus, proton, and neutron. Okay, so let's start at the beginning. So where we left off, Democritus and Dalton had kind of come up with the idea of atoms being small, indivisible particles, but we know that that's not true. So if we didn't discuss it in class, I'm going to go over it really quickly now. So today, the first two theories from Dalton are not valid. Why not? Well, if we look back up to his first two theories, it was that all elements are made of atoms. Indivisible is the key word right there. That is not true today. So we know that there is something smaller than an atom. Atoms are made up of tiny subatomic particles. And the other thing that isn't true today is that all atoms of the same element are identical. And what's different, you're going to maybe remember from physical science, is we have things called isotopes. And we'll get to that later in another video. So let's go back and see what are the contributions that scientists made in the 18 and 1900s that helped change Dalton's model. Okay, so let's talk about the subatomic particles. So there are three types of subatomic particles. They are electrons, protons, and neutrons. So these are the key vocab terms right here. So the first experiment is the cathode ray tube. And this is actually the technology that gave us the first types of TVs. If your grandparents have one of those really old big box-like TVs, they have cathode ray tubes in them. So Joseph John J.J. Thomson, our buddy old J.J. Thomson, he made an experiment. This is his experimental setup. You don't have to memorize that, but we're going to go through and talk about what he actually did. So cathode ray tubes, they produce a ray with a constant charge to mass ratio. That's the important there. He could measure the charge, he could measure the mass. All cathode rays are composed of identical, negatively charged particles, electrons. He discovered electrons. He didn't know it, but that's what he was looking at. And they were able to be deflected by a magnet. Electrons must be part of the atoms of all the elements. So how did he figure all this out? So inside the cathode ray tube, he had a vacuum. He had the source of the cathode ray. He shot the ray through here, and he put a charged plate. So we have a negative charge, and a positive charge. If that electron charge is negative, what do like charges do? Yep, like charges repel and opposite charges attract. So up here, if we have the electrons going through, it's going to repel and it's going to attract to the positive side. So if we're being pushed down and kind of pulled down, that means that there is some displacement, some deflection. So since this beam was moved by this positive and negatively charged plate, that means that he could actually measure the negative charge of those electrons. So his conclusion was electrons must be part of the atoms of all elements. This is the first time that Democritus and Dalton's ideas of the atom being indivisible were disproved, so we now know that they are made up of smaller things, but once you do get smaller than an atom, it's not the element anymore. Thomson also knew that an atom itself is neutral. So he knew that atoms are neutral. He also knew that electrons exist. So that means there must be some region of positive charge. This is where he came up with the plum pudding model. So what he said is that this is the atom. So here we have an atom, and it has these electrons, and they're like negative plums in a positive pudding matrix. Now, you probably have never eaten plum pudding, but think of it like a blueberry muffin or something like that. Or maybe like a chocolate chip cookie. So this right here is called the plum pudding model. Now, we know this is not right today, but it got us a step closer looking at the development of atomic theory. So that's our first experiment. Let's zoom down here to our second experiment in our timeline. We have the Milliken Oil Drop experiment. So this experiment, so Milliken, oops, why is that? Nope, my marker's messed up here. Let's see. Okay, now we're back. So, nope. Milliken, well, can't highlight, so we're just going to have to underline here. So Milliken, he was a scientist in the United States, and he came up with this really creative oil drop experiment. So he had an atomizer, which was over here, and that made a really fine mist of oil. And it was so fine that it was actually kind of little globs of electrons were firing out of the atomizer. He again put a positive plate and a negative plate, and what happened was he manipulated those charges. So even though we had gravity trying to bring those electrons down, the attraction from the positive plate and the repulsion from the negative plate made those electrons go up. He did a lot of complicated math that we're not going to go through and worry about, but he came up with that the electron is actually negatively charged. He knew that. He got some real numbers though. He found out that electrons are tiny, super tiny, so small that they're about 1/2000th the mass of a hydrogen atom. And here's that number, 9.109 times 10 to the negative 31st. Recall back our scientific notation, that means we've got to move the decimal this way 31 times. So that's a very, very small number. Okay, let's flip to our next page. So go to page 4. Okay, so now let's talk about the inferences from the properties of electrons. So what we came up with is that atoms are neutral, so there must be a positive charge to balance out the negatives. We don't know what that is yet, but we know something must exist. And electrons have very little mass, but atoms themselves do have a lot of mass, so there must be something else making up that part of the atom. Enter Ernest Rutherford. So the Rutherford Experiment took place in 1911, and Rutherford, he was a really dedicated guy. So what he did, he had this set up in a dark room. He had an alpha particle emitter, which is essentially a helium nucleus. We'll talk more about that later. So he was shooting these particles at a really thin sheet of gold foil, and most of them passed straight through. So he's sitting in a dark room, and when these particles hit the foil, it lit up, made a big bright spot. They sat there for hours and hours and days, and he kept seeing a bright spot on the back of the foil. But every once in a while, one would be deflected, and sometimes they would hit straight back at him. This was crazy. It broke all the theories of the day. I think the analogy was, he said it was as if like he shot a cannonball at a sheet of tissue paper and it bounced back and hit him. So what was actually going on? He assumed that the positively charged particles were bounced back if they approached a positively charged atomic nucleus head-on, like charges repel. So he had positive charges coming in. That's what all these lines are. The nuclei are very small and positive. Now, most go all the way through because most of the atom is empty space. But if he got a direct hit, that positive particle hitting a positive nucleus, it bounced back. So here were his conclusions. Very few particles were greatly deflected back from the gold sheet. So since most of them went right through, that meant most of them were traveling through empty space. So that means the nucleus is very, very small, very, very dense, and has a positive charge. Most of the atom is empty space. So if we sketched what his model looked like, we have a small, dense, positively charged nucleus, and then mostly empty space, and there's some of those electrons around. This is a big change from the plum pudding model, where he said, Thomson said, oh, there's just negative electrons in the middle of the atom, and there's a positive matrix, it's kind of solid. Rutherford said, no, mostly empty space, small, very tiny nucleus with electrons somewhere out there. So Rutherford's atomic model, he was the first one to come up with the nucleus. That is his most important contribution. He did not know about protons and neutrons yet. He said there's something in there, and later his students would come up and refine his model. So in the nuclear atom, protons and the neutrons are located in the nucleus. The electrons are distributed around the nucleus and occupy almost all of the volume of the atom. Rutherford, with his model, he couldn't figure out exactly where the electrons were. But don't worry, his student Bohr would come along later. We'll see this in chapter 4 and actually describe electron orbitals and how all of that worked. Okay, so that's where we're going to stop this video. The next video will pick up looking at actually going into the nucleus, looking at those protons and neutrons.